Good morning. Today we are doing Paul Hewitt's Conceptual Physics, Chapter 12 on the Law of Universal Gravitation. Now, Sir Isaac Newton was a genius who lived a few hundred years ago, and he was watching gravity the way babies watch all the time in every planet, every country on Earth, and he watched an apple fall. But he did something different than every other little baby and every other little person out there who's seen gravity. He said, what if the same reason the apple falls is the same reason that the moon falls around the Earth? So that is why we say Newton discovered the universal law of gravitation. He didn't discover gravity, everyone knew that. The ancient Greeks knew that. Ancient Greeks said things fall because Earth desires its own. So something came from Earth, it'll fall to the Earth. People came up with their reasons why things fall, that they knew matter is attracted to matter. But what Newton did was he said all matter is attracted to all matter. And the same reason the apple falls is the same reason that the moon falls around the Earth. So Newton drew in his little notebook, it's a famous picture now, he drew a picture of the Earth with a mountain on top. And he said, okay, we put a cannon on here, we fire it off with a certain amount of gunpowder, and our cannonball hits the Earth. He says, okay, put more gunpowder in there.
Hey, you didn't
Blast
do
it
the
much,
one with
much
the
faster.
moon.
We'll get there, sweetie. And now it hits that far. Now shoot it with a much, much higher tangential velocity. And it gets much farther. And you just kept positing. So what happens if we shoot it with such a strong tangential velocity that eventually we have something that just keeps falling and falling and falling and falling around the Earth and never stops falling, and that's the moon. So what Newton here posited is that the same laws that make an apple fall to the Earth make the moon fall to the Earth, and that things in orbit are really things that are just falling around the Earth. Because if you look here, the moon orbiting the Earth, you can see the moon is deviating from its tangential velocity. See, its tangential velocity would go in a straight line, right? This tangential velocity over here. And you can see the amount that it falls below its tangential velocity. Okay, let me draw that again. So, like the International Space Station.
Mom, you said something was straight and it was
like rockets, like any other satellite we shot up to the Earth. Okay, so here's the Earth, and we shoot things up, and say we've got this thing in orbit around the Earth, okay? If you look, the moon is falling the same way the apple falls to the Earth. It is falling, let me change that. It is falling toward the Earth, if you measure here, toward the Earth from what it would have liked to go. Its tangential velocity would have liked to go straight. So what the reason the moon doesn't crash into the Earth is it has enough tangential velocity that it is always missing the Earth. It is falling around the Earth, but fast enough that it misses the Earth. So, like with the cannonball, if you shoot with faster and faster tangential velocity, it falls farther and farther until it's just falling completely around the Earth. This is what we do when we shoot satellites into orbit. When Elon Musk shoots his the Starlink satellites, they're going around the Earth in low Earth orbit. What we do is we shoot them off with a strong enough tangential, we shoot them off with a strong enough tangential velocity that they're falling around the Earth and never if that Starlink satellite that's hurtling around the Earth, if you somehow smashed it in space, got rid of its tangential velocity, that satellite would just be sucked into the Earth. Same with International Space Station. The International Space Station is in low Earth orbit, falling around the Earth. If for some reason the International Space Station lost all its tangential velocity, it would come crashing to the Earth. It's like that when you put that, if for some reason us going around the sun, if our Earth going around the sun lost all of our tangential velocity, we would just get slurped in by the sun. Because the reason we're not the whole orbit is a dance. Orbit is a dance with a more massive thing in the middle is trying to pull that thing in. And that thing is going fast enough that it's constantly missing, constantly overshooting, constantly going round and round. It can't escape, it's in orbit. But if it won't be sucked in as long as it doesn't lose its tangential velocity. Yes, we can go watch Daddy. So an example, The orbiters are the survivors. Some people say, well, why is it when you look at the solar system, you just see things orbiting the sun? Anything that didn't have enough tangential velocity got sucked in by the sun a long time ago. I mean, maybe there was some, I don't know, giant thing that got sucked in by the sun. But we, Venus, Mars, Earth, these are the survivors. For like a failed satellite. Oh, for example, the difference between meteor that hits the Earth and a asteroid that, say, theoretically goes around the Earth, like you could say the moon is our giant asteroid that goes around us. The difference between that and a meteor is that the meteor didn't have enough tangential velocity. It got sucked in to the Earth. Where the moon is not an asteroid because it has enough tangential velocity. It's constantly going round and round and round. This is very similar to if you've ever seen like those donation, like to put a penny in for Ronald McDonald Child's Hospital, something. You know, there's signs outside of Walmart's, and they have this like giant funnel, and you put a penny in, it goes round and round and round and round, and then it goes down all these little gizmos and lands in. It's very satisfying. But when you see it going round and round that funnel, it's kind of like that planet in orbit, except that it doesn't have enough because friction and everything, it's losing its energy. It doesn't have enough, and it finally spirals down in. That would be like if a planet was losing its tangential velocity. I don't know, say if our planet was having to plow through an asteroid field, losing, with that friction with the asteroid field, losing more and more of its momentum, and then eventually just spirals into the sun. Okay, so Newton was this genius, and that what he didn't discover gravity. What he discovered was universal gravity, that he was able to say, what if it's the same law? And so he theorized that everything in the earth, everything in the universe, I should say, is attracted to everything else by the same law. And it's this: the force of attraction between two objects, I'll say mass 1 and mass 2, this is just a constant. We'll talk about this later. This is called the universal gravitational constant. Same for anywhere in the universe. You can measure it anywhere in the universe. It will be the same. This guy, G times the mass of object 1 times that mass of object 2 plus the square of the distance between them. So this means between me and the trash can over there. I could take the mass of me, the mass of the trash can, let's say about 15 feet away from the trash can. I plug that in, I square that, stick in the universal gravitational constant. I can find out the attraction between me and that trash can. There's an attraction between you and every other human on Earth. You just plug in your mass, their mass, and divide it by the distance between them, multiplied by the gravitational constant. The universal gravitational constant is a really, really tiny number. We will write this down. This is why the trash can doesn't come flying and hit me, because this is a very, very small number. It is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That's the universal gravitational constant. You can see it's a pretty tiny number, and because people don't like writing all these zeros, the scientific way to write this is you write 6.67 times 10 to the negative 11th. If you've never seen this before, negative 11 tells you got to take this and move it 11 times, and you get that. See, because it goes here 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 times. The tiny little number. This is why you don't just walk down the street and go, whoop, stuck to the person next to you, because it's a very, very tiny little number here. But you could see, even with this massively tiny number, you plug in your mass here, plug in the mass of the Earth. The mass of the Earth is huge. You plug the mass of the Earth in here, even with this tiny little number, you're going to end up with something you can measure. That's your weight. That's why when you walk down the street, you do worry about falling down and hitting the Earth. You don't worry about sticking to the people next to you. Okay. So, let's see. Oh, so because this gravitational constant is so small, that's why we say of the 4 basic forces in the universe, gravity is actually quite a weak force. It's that the masses are so huge, like the mass of the sun, the mass of a neutron star, the mass of the Earth, that's why we feel it. Compared to one of the other 4 great forces, the 4 basic forces of the universe, is electrostatic, electromagnetism. Electrostatic forces, electromagnetism, same thing, are quite strong. When you clasp your hands, the reason your hands don't just smush into each other is electrostatic repulsion. The electrons in your hands are resisting each other because matter is mostly empty space. We will get onto that later in the book. It's quite fascinating. So electrostatic forces or electromagnetic forces are very, very strong compared to gravitational forces where you've got that. Okay. Okay, so we've talked about how the more massive you are, so even multiply by this tiny little number, you put your weight in or your mass in, 50 kilograms, whatever. You put in the kilograms of the earth, this thing's massive, you start to see that number, even multiply by that tiny, tiny little number. You put in the mass of you and your buddy, and it's not enough. When you multiply by that, you can get a really weak force. You put in, the mass of Jupiter, you'll get something. That's why you feel the attraction to Jupiter. If you ever landed on Jupiter, you'll feel it. Now we're going to talk about here. The force of gravity on it is less the farther you are apart. So we'll see with the inverse, what we call the inverse square law, the force is proportional to 1 over r squared. So you'll see that the bigger this is, so let's say this is you being attracted to, I don't know, this thing. Look at this thing. Okay, so the thing is right here. There's, let's say, 1 unit of distance between you two. So we're going to plug that in. 1 unit of distance, so it's 1 over r squared, so this is going to be 1 over 1 squared. You have 1 unit of force between you and this giant tungsten core or whatever that is. Okay, now we're going to put 2 units. So that was, okay, so let's try to do 2 units. Okay, so let's say that was just r. Now this is 2r, okay? So now we're going to plug that in. Well, now we've got 2 squared. Okay, so now it's 1/4. So if you move the tungsten ball, just double the distance, you only get 1/4 of the force on it. Now let's move that tungsten ball. 1 more, okay? So now r is 3r. So you put 3 in there, 3 squared, 1/9. So if the tungsten ball is here, you're only feeling 1/9 of the force. Tungsten ball is here, you're feeling 1/4 of the force. So here you're feeling 1/9 of the force. Here it's 1/4 of the force. And here it's just 1 unit of force. And if we move it again, it's 4r. We move that tungsten ball 4r away. Okay, so now we've got 4 squared. We got 1. You only feel 1/16 of the force you did when it was only 1r away. This is the inverse square law. Another way to think of it is the further, yes, it's okay. The further away something is, so like think of it like a paint. You're spraying paint, and you've got a spray bottle of paint. You shake it up. You're spraying that paint. It's really, really thick, and it makes like a little circle on your page, right? You hold it out here. You spray it. You get a big, very light circle. It's diluted the farther away it is. That's what the force of gravity is like, or any force that goes by the inverse square law. The farther away you are, the more diluted it is. Like pulling that paint sprayer. Another way is back when they still do movie projectors. Like, they get one of those movie projectors and they hang up a white sheet and they shine it on. And the closer you keep that sheet to the movie projector, the brighter the picture is, the smaller it is, right? So you've got your movie projector and you're projecting. And so you've got 1r away. This is how big it is.
3 o'clock exact.
Okay, sweetie, I'll hurry up. You move it 2r away. And your picture is a lot bigger, but it's starting to get pretty dim. Well, no, not really dim, a little dimmer. You move that thing 4r away, it's like 16 times as dim. 16 times as big as it was 1r away, but it's 16 times as dim because it's getting spread out, it's getting diluted. That is what it's like with gravity because it goes by the inverse square law. So if we're going to chart, this is the Earth, we're going to chart what gravity looks like. Okay, so you're on the surface of the Earth.
It's taking too long.
You're on the surface. Sorry, sweetheart. You're on the surface of the Earth. You're going to feel gravity to a certain amount. The farther away you move, your mass isn't. The gravitational constant never changes. I should say the universal gravitational constant. When we talk about the gravitational constant, often we're talking actually about this. We're talking about the force of gravity on someone at the surface of their plane. This is the universal gravitational constant. Your mass hasn't changed. The Earth's mass hasn't changed, but your r has changed. So if you are right here, if you move out 2 radiuses, like 1 radius from the surface of the Earth, so 2 radiuses, this is going to be, your gravity is now going to be 1/4 of what your gravity would have been right there at the surface. So the farther you move, the weaker the gravity is. So if someone says, if you want to draw it like here, if you want to draw as a chart, this is the force of gravity at the Earth's radius, right here, the surface of the Earth. If the force of gravity is here, it's going to be falling by inverse. Actually, it looks a little more dramatic than that. So this is the force you feel. This is how strong gravity is, and it drops off the further you get by the r squared. That's why rocket ships, most of their fuel, they burn up right at takeoff. Most of their fuels, they're fighting this very strong gravity before they get out. That's where we use the term gravity well. If you flip this upside down, you imagine this is all the force you're fighting to get out. If you flip this force chart out, and you imagine it like this, Basically, to get out away from the earth, you're putting a lot more work. Here you don't have to put as much work in. You put a lot of work at the beginning. That's your gravity well, where you're fighting all that really strong gravity before you get far away enough that the gravity is weaker and it's easier to keep going out. Nice way to visualize this is sometimes they'll take like a ceramic, they'll take like a rubber sheet and then they'll put like a bowling ball in it or something to symbolize like the earth, and you've got like a little marble that's your satellite, and you'll see you've got to give it enough tangential velocity to get it up out of that well. Those it just kind of goes to the bottom of the rubber sheet where it's being pulled down by that bowling ball, and you've got to keep pointing it and get it faster and faster so it can go around and orbit. Okay, so everything pulls on everything. Everything pulls on everything by this law. That's what gravity is. Every piece, you can find out the attraction between you and Pluto. Plug in, universal gravitational constant, plug in your mass, Pluto's mass, and the distance between you and Pluto. And you'll see with that massive distance between you and Pluto, you're not really going to feel it. Okay. This is really cool. Since everything pulls on everything, so you've got the sun, huge and massive. And then you've got, say, our planets. This is not to scale because the distances are huge. Okay, so you've got, the planets going in orbit around the sun because, remember, the attraction between them and the sun. But as this one planet is going by on its orbit, another planet, they will be drawn to each other. Not to the scale that they're drawn to the sun, that's why they're still staying in their orbits, but they will be sort of pulled together by the universal law of gravity. And because they're pulled together, there's like a little deviation in their orbit. So instead of that smooth orbit, they kind of wiggle a little bit. This is how they discovered Neptune. Two different astronomers, I think there was a Swiss or a German one and a British one, both noticed that there was this wiggle in Uranus. And so they both did the math and they said, okay, if there's that wiggle, it's being drawn to something right about there. And then X marks the spot. And then they both sent letters to their respective countries', big telescope observation places. Said, please check the sky right about here. I think there should be a missing planet. And sure enough, that's how they found Neptune. Now, at the end of the chapter, he talks a little bit about the big crunch, Big Bang. Okay, so we know that the universe is expanding. So gravity, remember, pulls everything in, but something went kablooey, and the universe is going out, is expanding. This is something that's been, when scientists first started realizing the universe was expanding, this is right around Einstein's time, they really didn't like it. Like, really didn't. Like, even the phrase, the
Mommy,
Big Bang. Wait, I'm almost done,
outside?
sweetie. Yes. Even the term the Big Bang is an insult, I think, used by the enemies. Like, haha, you're acting like everything would start with the Big Bang. Scientists really love the idea of an eternal, constant universe. So much that when Einstein was doing the math and figured out that there was a beginning, he padded out his equations with the cosmological constant so he could say that the universe wasn't expanding because he really wanted an eternal universe. And then later, when they discovered, more discoveries, more math, more, when they measured the cosmological background radiation, there was no way around it. They had to throw away the cosmological constant. They're like, nope, the universe expanded. There was a beginning. For some reason, this really bugs a lot of scientists. I think it just offends their sense of the eternal universe being this beautiful, permanent thing. And so people have constantly tried to find ways around it. Now, the Big Bang is science. We've measured that with the cosmic background radiation. Sorry if I'm mixing up the words. We've measured that with the redshift of all the galaxies being redshifted away from us. Really cool stuff we'll hopefully get to next semester. But the whole idea, they said, well, maybe the world is expanding, but at some point it runs out, right? Because it runs out, and then gravity will take over, crunch it back down. Now the big crunch part, that's not, there is still like, if that's really going to happen, given like how much you've expanded out. Because gravity is this weak force. Is it enough to actually pull the whole universe back in together, or are things far apart enough by the time it slows down that it's not going to do that? But people like this, a lot of scientists like this idea of that, well, everything will crunch again, and then it will go back, and then it will crunch again, and then it will go back. When you get to this is something we cannot test. This is something that it just cannot be predicted, cannot be found. Like with Big Bang, we could say, okay, if this happened, we need to see this. And then we look for that, and yes, that's what we found. Because we're dealing with the entire universe has to redo and redo. At this point, it's more of religion. So the whole part where he's talking about the big crunch and the eternal Big Bangs going on and on, it's an attempt, I think, by a lot of scientists that really love the eternal universe to have a constantly expanding and rebalancing universe. This sort of kind of reincarnation feeling of it will always go on. this is more a religion than science, because it is not something that we can observe. It is not something that we can even make predictions about and see if those predictions are true. So when you start moving into like the big crunch, bouncing universes, multiverses, things that by definition are unobservable, we cannot come up with, you know, hypotheses and things to explain it, you're really more getting into the realm of religion. I mean, it's interesting. It's an interesting religion, but it's not really like the rest of the stuff we're studying here. I just wanted to make that clear because I think in the book he didn't really make that clear, that he was sort of going off into kind of his own philosophy and religion ideas.
Is it over now?
It was interesting. Yes, you can stop it now, sweetie.
No, but
Oh, my photographer wants to make an appearance. Hello, come here. This is this week's photographer. Okay, Pumpkin, can you go shut it down?
Ow! Wait, you think I was in the video?